we are going to talk about our loss function, which is called skeleton recall loss for connectivity, conserving, and resource-efficient segmentation of thin tubular structures. And basically by that, the first question which arises is, what are thin structures? What are thin tubular structures, right? And as a follow-up question, I guess, why do we actually care about that? As you can see here, as a kind of teaser imagery, you have vessels or streets in those images, and then the corresponding segmentation, which is thin structures, so lines, everything which is elongated, which connects A to B. And there you can already see why we actually care about those thin structures and getting them segmented. Because, for example, Google Maps, if they do aerial flyovers and segment the streets from raw images, you really want to have the streets connected, because otherwise your navigation won't work. And since we are from the medical area, we also want to have vessels or neurons connected to know which signal leads from A to B or which blood flow is going from A to B. And this is why this topic was kind of interesting to us, and we delve deeper into that. Looking at more examples, you can see that thin structures actually appear in various different forms and various different dimensionalities. On the left-hand side, you see 3D imagery from MRI scans, and in the middle is again aerial images and then retinal scans. And also a feature of thin structures is that you have very thin structures and thick structures, and sometimes even those in the same images. So thick structures getting thinner, and more like a lot of thin structures in one image, or just like a single thin structure in an image. And I mean, the field of thin structure segmentation has evolved quite a bit, and there are definitely a plethora of methods out there, but there is not really a method which covers all of those tasks at once, and especially the multi-class setting, which you can see on the left-hand side. And why is that? Well, basically, one of the reasons is that thin structure segmentation is actually quite tricky, because what you usually do is, with your normal segmentation loss, let's say dice loss, cross entropy loss, doesn't really matter. You have a set of pixels or voxels in 3D space, which you want to have segmented. So what you see here is a 3D scan of brain vessels, and this is the corresponding segmentation mask. And what you can also see in this image is that you have thin structures and thick structures in the same image, or in the same setting, so to say. And your normal segmentation loss would like treat this thick structure, all of the voxels or pixels in a 2D image, similarly to this thin structure. So let's say it kind of misses this thin structure, then it doesn't really care because it has enough voxels already covered in this thick structure. And this is why normal segmentation losses fail, and there's many ways out there to actually cover this and tackle this problem. So as I already mentioned, some of those ways can basically be classified into either the field of persistent homologies or something with skeletons or differentiable skeletons. I'm not going to go into detail into especially the left one. This is a very, let's say, mathematically founded approach, and you really look at the actual topology of your structure, of the ground truth or of the segmentation, and then you can construct some kind of barcodes, as you can see on the left-hand side here. And the idea is basically to really match the topology. So topology is the amount of connected components, the amount of holes, the amount of cavities from your ground truth to the predicted segmentation. And this matching, though being quite accurate, then from a mathematical standpoint, is super computationally expensive and doesn't really work for larger images, 3D or multi-class. And then there's the other avenue, which is differentiable skeletons. And for that, you can basically already see where the talk is going. If you look at aerial imagery, or basically the images I showed you beforehand, what we really care about is the connectivity between 2 points. So let's say we want to connect the hand and the feet of the football player. You don't really need the whole mass of the thorax right here of the body, right? You basically can just use the skeleton and walk that way, and you still have all of your connectivity. So that is why a lot of works just decided to use skeletons actually as some kind of way to enforce connectivity and thereby also integrating these skeletons into the loss function. And that's why you make them differentiable, or that's why many works try to make it differentiable. There's many versions out there, and basically the pros and cons of the methods are quickly shown here. As I said, persistent homologies are very accurate and topology focused, but then again, very slow. The faster alternatives are the differentiable skeletons, although they're still not really fast. I mean, they're like an order of magnitude faster than persistent homologies, but still slow, like double the training time at least, depending, of course, on the task, especially if it's 3D. And then again, by making the skeletons differentiable, you kind of lose accuracy, as we'll see later. So the skeleton is not necessarily perfect. And I think just last year at ECCV, there was a method published which makes a skeleton perfect, but this then again adds another layer of computational complexity. So you see where all of this is going. You either have the accuracy part or the computational complexity. One of the main methods we also compare against in our paper, and basically the whole field compares against, because it was the state-of-the-art method for a long time, is the so-called CL dice loss. I think it's just 2021 CVPR. And the basic idea is you pass your image through any segmentation network, and then on top of the dice loss or cross-entropy loss, you add this CL dice loss. And it uses their introduced skeletonization algorithm. It's an algorithm which can do a skeletonization in differentiable form, and it uses basically min and max pooling operations. You can imagine it as a kind of a erosion dilation operation, which is repeated with this ReLU in between, and then gives you a somewhat accurate skeleton. And this works quite well for specific images, especially in 2D, but also has its downsides. And the loss calculation in the end is then happening very similarly to the dice loss. You just focus on the center line. That's why it's called CL dice loss, center line dice loss. The idea is that you use the predicted skeleton, which you get by this differential skeletonization. So you use the prediction and then calculate the skeleton, so the center line, and you look at the overlap between this skeleton and the ground truth mask. And you do the other way. You look at the ground truth skeleton and the predicted mask. And this gives you, as they call it, topology precision and topology sensitivity. And then you can do an off-the-shelf normal dice loss calculation, which is then called CL dice. And this can be used as a loss function or as a metric. So really nice work by, I think, Shit et al. Yeah. And we still identified some problems, and also the field did, which is basically that the soft skeleton they introduced also introduces an overhead, which is kind of significant, especially for 3D. The skeleton is getting inaccurate depending on the image. I mean, you see a very bad case on the right-hand side here, where this 3D structure I showed in the beginning is actually kind of jagged and does not really look like a skeleton. And it's binary only. So you don't really have the chance to do this in multi-class because it just blows your GPU. So you get out of memory really quickly. Looking back at what we talked about so far, we have the main motivation for the paper that you want to have a structure which is thin and elongated, segmented. You cannot really use the dice loss, although it's resource efficient or can do multi-class, but it doesn't enhance your connectivity. Then again, the CL dice loss is at hand, which enhances your connectivity, but is not resource efficient and multi-class capable. And our skeleton recall basically we wanted to tick all the boxes right there. So do the connectivity enhancing and also the resource efficiency. And how did we do that? Well, I guess the main idea or hypothesis of our paper is that the ground truth skeleton is actually all you need. All the relevant topological information is in this ground truth segmentation, which you see in B here. Because the prediction of your network can be wrong and doesn't really contain too much topology information, whereas the ground truth is actually what you want to regress to. And by that, we designed a new type of skeleton, which we called the tubed skeleton, which we then incorporate into the loss calculation. The tubed skeleton is calculated by this algorithm. So basically what you have is your multi-class or binary 2D, 3D segmentation, doesn't really matter. And you first binarize it for the loss for the tube skeleton calculation, and then you skeletonize it. So on the right-hand side, you can see like this thin line in between. This is the skeleton of the 3D structure. And as you can see again, with this thin line, it is very thin. And it doesn't give a lot of signal if you include it into the loss calculation. That's why we tube it or we dilate it a bit, such that we end up with a structure which has the same topology, the same skeleton as the original structure, just the very same, so the accurate thickness of the structure of this tubing. So basically, everywhere you look at, the tube has the same thickness. And this kind of evades the effects of thicker and thinner structures I mentioned at the beginning. And the last step is just to multiply the ground truth segmentation mask again, so you get it in the multi-class setting. How do we incorporate this in the loss function? Well, basically, as the name suggests, it's called skeleton recall, so it is a recall additional loss. You have your generic loss function, similarly to CL dice, you have the dice and the cross entropy, and you add with a weighting factor the skeleton recall loss. And the weighting factor is in our terms just is most of the time just 1, but you can vary it if you want to do hyperparameter tuning. And then again, the skeleton recall function is just an additional recall on this tube skeleton. Putting everything together, what we have is the input image, which is passed through any segmentation network, and it produces a prediction. And with that prediction, we want to regress to a ground truth and do a loss calculation in between. Differentiable skeleton-based methods would do what we see as a kind of detour. You can see on the bottom here. So basically, you first have to calculate the differentiable skeleton of your prediction, and again, calculate the skeleton of the ground truth, and then do a loss calculation between those two, additionally to all the other losses, right? And all of this is happening on GPU and kind of makes everything slower. Whereas for us, what we do with our tube skeletonization, we pre-compute those tube skeletons. So all of this skeletonization is basically offloaded to either data loading or even before training. And then the only thing you have to do is add this recall loss between the tube skeleton and the prediction. And that's basically it from the method side.
Okay. Okay, so okay, so we've heard from Max about the idea behind skeleton recall and also the theory, but let's continue now with the experimental setup for basically all the experiments we did in the paper. So we always used a fixed segmentation backbone, which was most of the time in a UNet. And in addition to that, we also showed that it works and has all the benefits we shown in a UNet also on HRNet, but only for the 2D data sets. Then we always had a default segmentation loss function, which was dice and cross entropy loss, that was also fixed. And in addition to that, we had some connectivity enhancing loss function. So this was either just the default CL dice or what we call in our paper topo CL dice loss. So there was this method from Menton et al., which Max mentioned before, which introduced this topologically accurate differentiable skeletonization, and basically we replaced in the CL dice loss calculation the differentiable skeletonization with this accurate skeletonization algorithm. And then, of course, we also have our new skeleton recall loss as an additional connectivity loss function. We do all of our experiments on 5 data sets in total. So you've briefly seen already these data sets. So this was roads, so road segmentation on satellite images, then drive, which is about vessel segmentation on retinal images, and cracks, which is just the segmentation of cracks in any kind of concrete structures. And these were the 3 2D data sets we had, but we also had 2 3D data sets. These were challenge data sets from last year's MICI conference. And this was on the one hand top cow, so that was circle of Willis segmentation, so basically vessels in the brain on MRA images and CTA images. And then finally 2 very and that was about segmentation of the inferior alveolar canal, so basically a nerve in your jaw, and that was on 3D CBCT images. Yeah, and then of course, if you introduce a new method, you need to evaluate it in some way. So we used just because we are dealing with segmentation, and the default segmentation metric, of course, is dice to measure the overlap between prediction and ground truth. Then Max already mentioned that before in the CL dice paper, they introduced this loss function, but they also introduced it as a metric. So basically this metric measures the overlap between the ground truth and the prediction, but not basically just the normal overlap, but the overlap of the skeletons, basically. So this more or less measures the connectivity of your prediction, of the correctness of the connectivity. And then finally, we also had some more topological metrics. So these were the Betti errors and the Betti numbers. So basically the Betti errors are the differences between the Betti numbers between ground truth and prediction. And this basically, in simple terms, just measures different topological properties, like the lowest Betti number measures the number of connected components, then there's the number of holes in the segmentation, and then higher Betti numbers and higher dimensions measure more complex topological properties like cavities and so on. And yeah, before I show you the whole results table, because it's quite big and maybe not nice to look at directly, I'll show you first just for the results for one data set to show you what you'll see in a second. So we always show basically just the default and a new net result. So that's just with dice and cross entropy. And then we show also the results for the additional topology loss functions, so CL dice loss, topo CL dice loss, and of course our skeleton recall loss. And we show the results for all these four metrics, which I talked about a second ago. So dice for overlap in green, CL dice for the connectivity, and then the Betti errors for the topology metrics. And as you can already see here, just for this example of a roads data set, on this data set, we outperformed all the other methods on 3 of the 4 metrics we are looking at, and were quite competitive on the Betti 1 error. And yeah, as I already mentioned, the whole results table is quite large. So let's go through it step by step. So the most important finding was that we actually outperform all other methods on the CL dice metric on all of our 6 data sets. So that really shows that our skeleton recall loss is really good at this connectivity conservation, which we actually designed it for. On the left to the CL dice, we also see that on 5 of the data sets, at least, we perform the best on the dice metric. And on the drive data set, we are only slightly behind the CL dice loss. And looking at Betti errors, we also either perform best or at least comparable to the other methods we were looking at. And a few more things you can see from this results table. So I mentioned before that we are comparing against topo CL dice loss, but as this introduced this new topologically accurate differentiable skeletonization algorithm, that introduced a lot of additional overhead, and therefore it was only feasible to do that in 2D. It was completely infeasible for our 3D data sets, unfortunately. But that's why we only have results for that on the 3 2D data sets. And if you look at the multi-class setting of TopCar, which is the last data set we have here, you can already see that for CL dice loss, that actually ran out of memory. So we trained that on a A100 GPU with 40 gigabytes of VRAM, but it was completely infeasible. And we'll also see more on that in a second. But first, for the basic single class experiments, let's look at the resource efficiency, because that was one of our main motivations actually, in combination to the inaccuracies of the skeletonization of CL dice loss. That was really a problem we had when we experimented with that, because we found that it's really, really inefficient to train CL dice loss. And you can see it in these two plots. So on the left, we have training time per epoch, and on the right-hand side, we have the ReRAM consumption during training, and the kind of shaded areas at the bottom, that's always the NNUnet baseline. And then in green, we see the skeleton recall, and in red, we see CL dice loss. And as you can see on both plots, skeleton recall introduces only very slight overhead, if any, and mostly that's during for the training time, because there's the additional loss calculations that introduces some overhead, but also for some reason for TopCow, the ReRAM consumption slightly increased. But in comparison to that, CL dice loss really introduces a significant overhead, which is sometimes more than a factor of 2 if you look at the training time for the drive data set. But also if you look at VRAM consumption for tooth fairy, for example, the VRAM consumption is increased by nearly 7 GB with CL dice loss. And that really shows how inefficient it is. And that's, of course, if you want to train stuff, really undesirable, because, I mean, it's obvious you need bigger GPUs, it trains for longer, and therefore that was really undesirable. And by the way, if you're wondering why we only compare against CL dice loss, this plot really nicely shows that. This is from a recent publication by Lux and Berger et al. And they introduced this method topograph, which is also a topology conserving method basically for segmentation, but only in 2D, because it's also really inefficient. And they had this plot in their paper which shows basically the runtime for all these different methods. And these are methods with persistent homology and Betty matching and all these more explicit topology conserving methods. And as you can see here, if you look at this kind of methods, CL dice is like the clear winner when it comes to resource efficiency by more than 1 order of magnitude. But that, of course, meant for us that it's completely infeasible to compare against all these other methods, because they just are so inefficient and don't work at all if you go to 3D. But with that, after that quick detour, let's come back to our comparisons. So as I already mentioned, and as you've seen in the results table for the multi-class setting of TopCow, so that was with 13 classes in total, CL dice loss completely went out of memory on the A100 GPU. And so we looked a bit more in detail on the resource utilization depending on the number of classes we have in our training. And we did it on TopCow, and you can see in these two plots the VRAM consumption on the left and the time per training epoch on the right, depending on the number of classes in our training set. And this is shown for batch size 1 and 2, but the details are not that important. But as you can see here, basically the overhead introduced by skeleton recall is constant, and it's completely independent of the number of classes. It's just this additional loss calculation, which takes a few seconds maybe in total per epoch. But apart from that, it's completely constant, and therefore you can train with an arbitrary number of classes. But for CL dice loss, there's not only this huge increase both in training time and VRAM consumption that we saw in the single class setting, but that's actually added basically per class. So it's nearly a linear scaling in VRAM consumption and training time. And this, of course, explains why it went out of memory on the TopCow data set, because you can train maybe with 6 classes on an A100 GPU, but that's already stretching it really by a lot. But now that I've shown you like the results we had in our table, and of course that's always something we do and we compare against other methods, and yeah, it's always nicer to see it like in a real world setting. So I'll show 2 examples here. During the time we developed skeleton recall, or actually the data sets which led us to developing skeleton recall, one of these was TopCow from the TopCow 2023 challenge. This was the one with vessels in the brain, and we were actually able to win this challenge using our skeleton recall loss. And I think we won first place on 3 of the tasks and second place on the last task. And what was really interesting to see this year, there was another iteration of TopCow, and we gave a quick or short keynote during the challenge session. And the winners from this year, they actually also used skeleton recall, and then in addition to that, they also annotated some cases for themselves to have more ground truth samples to train the method. But they basically, from a methodological side, just used our method, and that was really nice to see. Yeah, and the other data set was Tooth Fairy, that was with the nerve segmentation in the jaw. And yeah, there we were actually able to reach the second place with our method. Yeah, but finally also some qualitative results, because all these numbers are nice, but as we said, it's basically irrelevant for these downstream tasks. And these downstream tasks, they all care about connectedness. So structures need to be connected to ensure blood flow, or yeah, route planning if you look at roads. And as you can see here, we have on the top, it's Tooth Fairy, on the bottom, it's TopCow. And skeleton recall really closes the gap we had in some of the predictions from other methods on these data sets. And this is also the case for these 2D data sets. And yeah, especially here, you can really see how relevant it is to really capture basically the whole structure, the whole skeleton basically, because otherwise, yeah, your downstream application will really fail. And yeah, basically we had examples for all of our data sets where skeleton recall was really able to improve these previous errors from other methods and improve the segmentations that close gaps from other methods. Yeah, and then finally, after we published the paper for ECCV, I think it was in the summer, one of our collaboration partners from Munich reached out to us, and they had the problem of segmenting some vessels in mice lungs. And there they also applied our skeleton recall loss and tried it out. And yeah, this is basically the result of it. In yellow, you can see they're just using dice and cross entropy loss and using skeleton recall loss on top of that. There we agree. And red is basically the stuff which skeleton recall captures in addition to the method with just dice and cross entropy. And you can really see here that skeleton recall is able to segment all these small, thin, intricate structures, but they are really small, but really important if you look at any downstream tasks. And that was really nice to see that it also worked for this downstream data set we didn't even touch at all. And it was basically just applied out of a box to this task. So that was really cool to see. Yeah, and after showing you all these results, let's come to the conclusion. So first of all, we showed with our skeleton recall loss overall superior performance compared to the existing state-of-the-art topology-aware loss functions. We do this by introducing only minimal additional training time and memory, especially if you compare to CL bias loss and yeah, basically other competitors. And most importantly, we actually introduced the first loss function, which is specifically designed for computationally feasible multi-class segmentation of all these thin structures. All previous methods designed for thin structure segmentation basically fail if you go to the multi-class setting. And yeah, with that, I want to thank you all for your attention. You can reach out to us by just scanning these QR codes, or I think there will probably also be some links somewhere. And yeah.
Yeah, so we did have a question about the playbacks. Yes, they're going to be available, as well as all the resource links in the follow-up email in your inbox. We did have one question about getting access to the code, the bits, and maybe the data. Two places that I sent people were one to the actual paper and second to the GitHub repo. So if Max or Yannick, you have additional links that you would like to share with folks beyond the GitHub repo or the actual paper, drop those in the chat. But it does look like we have 3 questions in the Q&A queue, if you want to hop over there. One appears to be kind of a more general question about your field of study, but then there are 2 other questions that came in, Yannick, in the early part of your portion of the presentation.
Okay, so this
The second one first.
Yeah. Please explain the use of the term differentiable in this case. Yeah, so basically differentiable here, it's just you need to use it in the loss calculation. So basically you can't do the normal hard skeletonization, which you would do with like erosion operations. But that's why CLI's loss, for example, opted for this min and max pooling. Yeah, so that you can then in the end calculate a loss, which of course needs to be differentiable.
And I think the more general question is it can be easily addressed. So basically, we are PhD students doing our PhD in this work group, and it is not necessary to join our group, or I think many medical groups having medical knowledge. And you can just easily work your way into that. I mean, if you especially come from the main computer vision domain, I guess the other way around is harder, coming from medical to main computer vision. And this is why we also try to keep doing both. And as you can see, I mean, it has a heavy medical focus, but it's still working for normal computer vision tasks. The last question. So I'm not 100% sure what you mean by different viewpoints. I mean, this is a 3D segmentation, and if you look at it in 3D, then you can see, I guess, better which part does work or didn't work. But I mean, maybe you can write a follow-up question, what you mean by different viewpoints, but because I'm not 100% sure what you mean with repeatability here.